And I'll discuss all the important questions which are essential from this first cumulative test. Check out. The Newman projections of PQRS are being shown, and we need to identify the correct statements like PQRS represent whether they are identical sets or not. What is the IUPAC name of Q and R, and whether all the given molecules are achiral or chiral, and lastly, RS positions, R and S positional isomers are there or not. Okay. So, so given key, you can see it was B, C, D. These are the correct statements here. So first, one way to look at this is um, I can write the Sawhorse projection and then figure out what is the difference there. So you can see Sawhorse projection can be like this. On the back side, we can have this way. We have methyl and ethyl C2H5, and this is on the front side. On the back side we have OH, methyl and methyl, this way. Okay, so if you run through the number of carbons, we have 2, 3, 4, 5. So I would write this as 5 carbons first, and on the fourth carbon I have a methyl and OH, and on the CH2 third carbon I have two methyl groups on it, right? uh, Now you can see this bond and this bond is the same thing. Okay, so this is how I'll try to write everything and check out. That is my way of solving. I mean, that makes me much easier to identify the compounds. Okay, the second thing also I'll do the same thing here. You can see first I'll write the Sawhorse projection. Here we have two methyl groups with some OH here, this way, and we have H and ethyl, and backside I have hydrogen, hydrogen and methyl. Correct. So if I count the number of carbons from here, you can see there is ethyl. So 2, 3, 4, 5. Again, I have 5 carbons here, like this. And on the third carbon here, I have connection to one carbon which has two more carbons and one OH group on it. Rest all are hydrogens. So this is the second structure. Third structure, if you notice, we have, you know, the front carbons like this, back carbons this way. We have a methyl, methyl and OH. Backside we have ethyl, hydrogen and ethyl. So I'll start from ethyl. Ethyl is two carbons, 3, 4, 5. Again, you can have this as 5 carbons here. And on the first, on the second carbon from here onwards, we have a methyl also and OH also. And the next carbon we have another ethyl group like this. That's it. These two are the, this is the compound for the third one. Last one, you can notice that we have this way with ethyl, isopropyl, hydrogen, and sorry, not hydrogen, OH. And on the front side I have methyl, hydrogen and hydrogen. So you can see, if you check out the number of carbons, it is 1, 2, 3, 4, 5. So we do have 5 carbons here, and for second, third. On the third carbon, we have an OH and another ethyl group. And on the fourth carbon, we have a methyl group this way. Okay. Now, check out how P and Q are initially. You can see for these cases, you need to check out for the longest chain. Write the IUPAC. One second. Sorry. Right. Sorry. Check. So you just need to figure out the number of carbons here. So you can see 1, 2, 3, 4, 5. This is the longest chain. Here 1, 2, 3, 4, 5. This is the longest chain. 1, 2, 3, 4, 5. And here we have same one from this end onwards. 1, 2, 3, 4, 5. So IUPAC wise, these are the numbering which you will do. And now you can map up and see how they are related with each other. Okay. In that sense, if you notice, B, C, D are matching. Clear with the first question, everybody? Any doubt you have, you can ask me right now. Right. Second question, I think this should not require much of explanation. I'm skipping it, but if look at this, if anybody has a doubt, you can just put a thumbs up. I can discuss. Okay. What are the questions I'm skipping? If you feel like you want to discuss, just put a thumbs up. Next, third question. Which of them are being identically matched here? Okay, so check out first one. Here, if you notice this one, which of them are correctly matched? So first one is definitely not, because if you notice here, all three OH groups, sorry. Oh, first we need to bring the methyls on the same position. So then only we can decide. So you can see this same structure I'm writing in a Fisher projection once again. Okay, by making an even number of exchanges. If you could recall, if you want to get the projection, you have to make even number of exchanges. So these three carbons, I'm trying to use them for making an even number of exchanges. So methyl here, hydrogen here, that is exchange number one. Hydrogen here, OH here, that is exchange number two. So OH here, H here, and methyl here. So this is what you get. And then OH on the left, H on the right. Same way, you can see methyl down, OH up, that is exchange 1. OH here, H here, that is exchange 2. So OH will come on the left, H will be here, methyl will be here. Now what you need to notice is there is a plane of symmetry on this Fisher projection as well as on this Fisher projection, which means this is a mesoform, this is a mesoform, and both of them are mirror images of each other. Meso, which are mirror images of each other, are always identical. So A is correct. Okay. I guess this question is clear, everybody. So this is how you look into it. Clear? Now check out the second one here. You need to convert this particular structure into the Fisher projection. So what we can do is we need to get ethyl here. So start watching the molecule from the top. As you watch it from the top, then methyl will be here, ethyl will be here. Bromine is on the right, chlorine is on the left, H is here and H is here. Correct? This is how we have the molecule here, because when you are watching it from the top of it, this Br is coming out of the plane, so that will be on the right. Chlorine is also coming out of the plane, that will be on the right. So rest of the two will be on the left here. So they are looking out to be identical, so that is correct too. Okay, next check out the third one. Okay, third one, if you notice, these two are geometrical isomers or not. See, if you notice carbon 1 and 2 position here and carbon 1 and 3 position here, the minute carbon position, I mean the functional groups or any substitute positions changes, then they become structural isomers and not geometrical or stereoisomers. So C is incorrect. Okay, then if you notice D, if you want to check out the IUPAC name, acid is the main functional group. So 1, 2, uh, these two are the carbons here. And how do we read about this one now? So this is C. There are two carbons, so it is ethan double bond O. Double bond O is ethanoyl. Okay, and then it is connected to oxygen. So oxy. So there is an ethanoyl oxy on the second position, and that's what it has been written, so which is correct. So I think the third case is clear. Third question is clear, everybody. Right. Next. Which of the following is a molecule which is chiral? We need to identify the either chiral centers or an asymmetric positioning here. Okay, that is what we need to check. So check out first one. You can clearly make out that here there is a chiral center, here there is a chiral center, and there is no plane of symmetry. So definitely this is chiral. Second one, even if you try to make any plane passing through this like this here, like this, if you make this as a plane, still there is a methyl here and nothing here, so which means there is no plane of symmetry here. So as a overall molecule it is chiral. Okay. Next, if you notice this, suppose if I make a 180-degree turn here, so methyl will be here, chlorine will be here, H will be here. So what is this form? This is mesoform, so this is not chiral. So how many? 1 and 2 are chiral. Sorry, 1 and 2 are chiral. Next, I'm skipping this. I'm sure you guys can identify that easily, whether they are functional diastereomers or enantiomers. But if anybody want me to discuss, I can. Please check everyone. Now, nobody raised their hand, so I'm going for the next one. Which of the following are correct about the given structures here? Again, this is very typical of it, but I'll still, show you how we need to write it down. So first, if you notice the first structure, we need to figure out whether uh, structure 1, 2, 3, 4, which can show optical isomerism, conformational isomerism, geometrical isomerism, and so on. This is what we need to figure out. Okay. First one. Uh, go with the options was first, everybody. Whichever the options are given, only look over for that. Okay. Structure 1 can show both optical and conformational isomerism. Okay. Let's see whether this is correct or not. So structure 1, we have no chiral center here. Backside carbon also no chiral center. So first option is incorrect. I mean, this B statement is incorrect. Nothing has been asked about structure 2, so skip it. Come to structure 3. Structure 3 can show geometrical isomerism and optical isomerism. With respect to this particular center, methyl is up, but there is no other group to identify cis and trans isomers. So this is also incorrect. Okay, this cannot show any geometrical or optical isomers. Okay, just a second. Right. So next, structure 3 can show optical isomerism, which is correct because there is a chiral center here. And structure 4, this is an alene form, shows geometrical, which is incorrect because these two are the hydrogens, which does not have any cis and trans correlation with the other two. So this is also incorrect. Okay. So I guess all of you must be comfortable with this question as well. Right. This also I can skip it, but if anybody wants to discuss, please let me know. Everybody's comfortable with this question. Seventh one. All good? Right. Number of pairs of enantiomers possible with C5H12O. Okay. So we need to basically just write the uh, alcohols and ethers which are possible with this molecular formula. And out of that, you can clearly notice that these are the four which are possible ones. You can just have a look at it. Does not require much of a discussion, I suppose. Come to the next one. Identify which shows geometrical isomerism. This I'll definitely discuss. Okay. So you can quickly check it out. What are all the options which are okay? Check. First one. Here with respect to these two, I can have cis and trans isomers. So definitely yes. Second one, same logic. Here with respect to these two stereo centers, I can have geometrical isomers. With respect to double bond, NH also a lone pair and OH will act as two different groups here. This can show geometrical isomerism. With respect to this double bond, it can show geometrical isomerism. With respect to these two, yes. With respect to this also, yes. Here also it shows geometrical isomerism because one is lone pair, the other one is the rest of the group. Okay. Here also the same logic, but left hand side it cannot show. So this does not show any geometrical isomerism. Here left and right both cannot show because there are no two different groups. Okay. And you know that allenes, the even number of carbons will always show geometrical isomerism as long as groups are different. So this one will show definitely. This will not show groups are different, but this will only show optical. Why? Because it is an odd number allene, odd carbon allene. Next, here, with respect to this, it does not show anything, but here, with respect to these two stereo centers, it can show cis and trans isomerism. This it can definitely show because this is a cis form. If I put the same double bond here, it will become a trans form. Here also, with respect to these two, it can show geometrical isomerism. So yes, this one also will show geometrical isomerism. So you can count the number now. So basically it is 1, 2, 3, 4, 5, 6, 7, okay, 8, 9, 10, 11. No? These are the ones which can show geometrical isomerism. How many of the following are matching, correctly with the given options here? So let's look into this part, whether they can act like metamers or not. First one. Uh, you can see here basically it is an ester. Here also it is an ester, correct? So as long as the functional group is same and the group only it is changing because of the uh, relative difference in the number of alkyl groups, then we call it as metamers. So definitely these are metamers, okay? And second one, you need to figure out the IUPAC name. So numbering should start from double bond because double bond should be given the more priority in this case. So I can start from here 1, 2, 3, 4, 5. Okay. So sorry, not like this. Sorry. Okay, this way. If at all I started from here 1, 2, 3, 4, 5. This way I could start. Okay, because that's the only way we can get the least numbering here. Got it? So this is incorrect. Okay, because double bond should be always getting the least numbering or least locants. Third one, IUPAC name of this one is okay. This is an anhydride, so you can start numbering from this side 1, 2, 3, 4 like this, or you can start with 1, 2, 3, 4 like this. Okay, so but to do that, we need to check out that naming wise which one is coming first. Got it? I mean alphabetically, which is coming for this is coming A and this is formula F. So alphabetically A will come first. So the correct numbering will be 1, 2, 3, 4. Hence it has to be 2 amino, 3 formyl, and it is butane, correct? 1 and 4 dioic anhydride, which is correct. So this IUPAC name is correct. Next, isomers of butanoic acid is ethyl butanoate. So which is true because this one as well as double bond, sorry, as well as double bond O and like this. So these two are one and the same. Next, E. These two, if you notice, CH3H, CH3 here, and backside we have Cl, H, and OH here, correct? Now, if you basically just tilt it around, okay, so why don't we just tilt it around and write down like this? and like this if at all I put it, correct? So I can say that methyl is up, H is left, OH is right. Same way, chlorine is up, H is left, OH is right. This way, correct? Now, if at all I write it as the mm, uh, of if at all I write the Newman projection, for doing that I can just rotate it around by 60 degrees. So if I rotate this by 60 degrees, you will get OH down, right? OH will be down, Cl will be here, H will be here, correct? And CH3, OH, CH3, H and OH. Yeah, this is how it is present. Correct. So now, if you notice the backs, compare that with this one here. Okay, compare that with this one. So you can see H and Cl and OH. There is one exchange which can happen with respect to this structure, and here also there is one exchange that can happen. So that means the front carbon and back carbon will require only one exchange. So one exchange will always lead to formation of enantiomers. So that is correct. Clear? Any doubt on the 10th one? Please let me know. 11th one. Let me discuss the 11th one also. Which of them are being chiral here? So first one, because of the odd number of carbon alene, it is chiral. There is no chiral center here. This one has a mesoform, so this is not optically active. Next one, here this is optically active because this does not have any plane of symmetry. Here, this is more or less like an alene form only. You can write this as virtually this kind of compound here, correct? So which is same as the alene form, so it shows optical activity. Here there is a chiral center, correct, which is very different from the others, so definitely optical activity is observed. Here there are two chiral centers and no plane of symmetry, optically activity is observed. And here there is no chiral center, so no optical activity. Okay, so how many did we get here? So one, two, three, four, five. So five of them. Yeah, I guess this part is clear, everyone. How many aromatic structural possible for this one? I think this is just a permutation you need to look into. So I'm not going to discuss much about it. But if anybody wants to look at it, please check the solution ones. Done? Right. So the next one, how many esters are possible with C4H8 and O2? Okay. So how many esters we can make? See, we have four carbons. So start with hydrogen only, everybody. Like this. So with hydrogen, which means double bond O, O and 1, 2, 3. Then hydrogen and double bond O and like this. And then hydrogen, now the hydrogen case is done. So start with CH3. So CH3, C double bond O and 2 here. And do with the third case here. So C double bond O with O and methyl here. Only how many we can get? 4. Please notice that, everybody. Next. Again, this is more or less very straightforward question. If anybody wants a discussion, I can do it. Otherwise, we can skip it. Check out 14th. All okay. Next, check out 15th one. Okay. 15th one we can discuss just because of the definitions, correct? So look into it. What is the kind of options we are supposed to get? First, we need to read about meso, enantiomer, and racemides. An equimolar compound mixture of enantiomers, that is definitely racemization. Stereoisomers that are not mirror images. Not mirror images are definitely diastereomers. Non-superimposable mirror images are enantiomers. Optically inactive compounds whose molecules are chiral even though they contain chiral centers, that is meso. All good. Next, check out 16th one. Again, 16th one is very straightforward. If anybody wants a discussion, I'll do it. Otherwise, we'll skip it. All okay? 17th one, please check. It's just about identifying, you know, chain, positional, functional, and metamerism. Again, a straightforward question. All okay? Right. Now, let's see the next paper. See the first one now. Check out. The maximum number of possible isomers that include stereoisomers, which may be formed on monochlorination of 1-methyl cyclohexane with chlorine and so. Okay. The usual technique is, for these kind of cases, because it is an allylic substitution. Okay. Because wherever there is a double bond, you'll always refer to go for an allylic substitution first. Got it? So you do the allylic substitution first, and then you do the normal substitution, everybody. Okay. Acha, if it was only NBS, mind you, if the question was given NBS, then you will do only allylic, you will not do others. So what I would supposedly do, see, if you have a double bond like this, correct? I will notice first all the allylic positions. You can see this is one allylic position, and this is the second allylic position. This is the third allylic position. Then I will write their respective resonating structures also. So double bond, dot, and double bond and dot. Okay. Then I'll see structurally if any of the structure is same or not. So you can clearly notice that this compound and this compound are structurally exactly same. So you can skip these two while discussing the number of isomers. I mean, you can take only one of them. Okay. So you can see 1, 2, 3, 4, 5. You will get 5 different structural ones, right? So write their respective products now. So first we will write this as chlorine here, chlorine here, chlorine here, chlorine here, chlorine here. Structurally, the allylic compounds are being done. Next, what I would do, now I will go for rest of the positions which are there. Okay, which are non-allylic. Non-allylic position is this one, then this one. Here is the other non-allylic position. Okay, so only on these two positions I will add two more compounds here, so which includes chlorine here, and then I will go chlorine here. Okay, please follow the similar algorithm so that you do not skip out on anything. So now you go back and notice how many uh, stereoisomers you can get. So in the first case you'll get only one, but here because of the chiral center you'll get two. Because of the chiral center here you will get two. Again a chiral center, so you'll get two. Again a chiral center on this position you will get two. And now here is also a chiral center, you will get two. Here it is again a chiral center. Notice this carefully. This is also a chiral center, so you'll get again two. Okay. So in short, you'll get 2, 4, 6, 8, 10, 12, and 1, 13. So please notice, if there is any doubt, you can ask me now. Everybody, all okay? Done. Check out the next question. How many of the following compounds have intramolecular hydrogen bonding? Okay. O nitrophenol definitely will have. O hydroxy benzoate ion definitely we will have. Correct. Okay. Next, ortho hydroxyphenol that also will have. Okay. Malic acid. Okay. Now malic acid is what? Like this. C double sorry double bond like this. C double bond O, O and H here like this, and C double bond O and uh, sorry, I'll write it this side. Okay, O O H here. Sorry, correct. Double bond O O H here and double bond O here. While this one will have like this O and H here, and this one will make a hydrogen bond. So this is malic acid. Fumaric acid, double bond will be here. This is malic acid, by the way. Fumaric acid is an transform of this butadiene. Okay, butene. Okay, 2 butene. So definitely this will not show intramolecular. Chloral hydrate. Everybody remember the wording from now. Okay, chloral is CCl3 having C, O and H, O and H, and this hydrogen. So here there is a hydrogen bonding as well. In fact, within the organic compounds, within the molecule, if you have chlorine and hydrogen, that is also considered as hydrogen bonding. Okay. Next, uh, acetone. Acetone does not have any hydrogen bonding. Fluorobenzene does not have any hydrogen bonding. Ethyl acetate, double bond O, like this. This does not have any hydrogen bonding either. Okay. So this one is yes. This one is yes. No, no, and no. Okay. I hope all of you got the idea which of them are intramolecular and which does not have intra at all. Clear? How many of the following structures the direction of the inductive effect is correctly matched? Okay, it's very good one. So you can see inductive effect of the compounds is correctly matched, which means whether they are trying to give away electrons or whether they are trying to take away electrons is what you need to check based on electronegativity. Oxygen is more electronegative, so we do expect that to take the electrons, so it should be opposite way, so this is incorrect. Cyanide is pulling, that is correct because cyanide is strongly electronegative. Carbon is pulling, which is correct because carbon is more electronegative than lithium. NH3 plus is strongly electronegative, so that is pulling, which is correct. Okay, then if you notice that double bond O is pulling, here O is also pulling, which is also correct representation. Okay. Here, this one is pulling is incorrect because this is sp carbon, this is sp2 carbon. Pulling should have been like this. Next, fluorine is for fluorine will never pull, it will be always on the opposite direction like this. So this is also incorrect. Okay. This one are incorrect. So how many we can got it correct here? So four of them. Okay. Ambidentate nucleophiles, I think you can see the list. I do not require to explain much of it, so I guess you should be okay with it. All good. Next, the positive charge on the carbon can be delocalized over how many oxygen atoms in the resonating structures. So you can see how many oxygen atoms will be in the resonating structure here. Okay, right. So let me show you where the positive charge can go. So one by one, we'll start with this one. See, pi bond move here, positive will come here. Pi bond move here, positive will come here. Pi bond moving here, positive will come here. Pi bond moving here, positive will come here. Now look at the other side. Pi bond moving here, positive will come here. Pi bond moving here, positive will come here. Pi bond moving here, positive will come here. Okay. So now you need to figure out uh, over how many oxygen atoms in the resonating structure. Now notice this lone pair will be involved in resonance. Tick. This lone pair will be involved in resonance with positive charge. Tick. This lone pair will also be involved in resonance. Positive charge. Tick. That's it. These three. Very simple but yet very effective question, because conceptually you will get to know the directions, how the resonance work, okay, how the lone pairs are involved. Okay, I hope all of you got this. Any doubt? Right. Number of compounds which are more basic than aniline. Okay, so aniline is like this. Now remember that aniline has a delocalized electron, so keep that in mind. Next, if you have any extra methyl on it, that will make it more basic. N-methyl ethanamine, that will definitely be more basic because it is localized. Acetanilide, amides will be extremely weak bases like this double bond and sorry, NH. This is the structure of acetanilide, double bond. Oh, this is an amide which will be very weak basic. O-tolidine, O-tolidine is like this, which have NH2 and CH3. This is very interesting. See why, if you compare these two here, it appears like methyl is actually donating, but on the other hand, it is causing something called ortho effect. Because of ortho effect, it would be less basic. 4-methyl aniline, definitely this will not have any ortho effect, so this will increase the basic character. Benzylamine, localized. Benzylamine means like this. We have a CH2, then NH2, so it is localized electrons. Ammonia, definitely more. Benzamide, again, it is an amide form, so definitely least basic of all. Got it? So five are the compounds which are more basic. Next. This I don't need to discuss. I suppose all of you can get that answer. Total number of products obtained by monochlorination of S-chlorohexane. Very important question. If you haven't done correctly, please check this out carefully while making the number of connections. See, we have 1, 2, 3, 4, 5, 6 carbons. How would I do the working? Check it out. 1, 2, 3, 4, 5, 6. And now I know that one of the chlorine is fixed. Now I have to start placing the second chlorine. Okay. So now what I'll do, I'll take these structures and write as many structural products as possible. Now notice which are all the structural cases. One chlorine here, one chlorine here, one chlorine here, one chlorine here, one chlorine here. Okay, and lastly, structurally, when I write one more chlorine, these two chlorines will be on the same position. That's it. Structurally, this is how much you will get. Okay. Now notice, okay, here this is the carbon chiral center which is fixed. So you'll only count it as one compound. Here we have two of them. Okay, you will get two of them here, correct? So one will be on the same side, one will be on the opposite side. So I'll get only two. Here again there is a chiral center. You will get two, correct? Here also there is a chiral center. You will get two. Here at this position you do not have any chiral center, so you will count it as only one. And here there is no chiral center, we count it as only one. Okay, so please check. These are the structures we need to count. Now you know what will be the more interesting question here, everybody. How many number of compounds which are formed are optically active? If the question was, which of them are optically active? Now this becomes very interesting question. Check out. First one is optically active. Okay, this one I'll write it as A B C D E F. Okay, A B C D E and F. So you can see A is definitely optically active. E has a chiral center optically active. Okay, and now when it comes to B, at this position, one chlorine which is R configured, if that is optically active, then S configured will not be optically active, because that S will make this also will become S, and both will have a mesoform. Hence only one of them you have to count. B you have to count only one. Here also one. And in C you will count it as both being optically active. D you will count both being optically active. That's it. Okay, clear? F is anyway not optically active at all. Clear, everybody? Right. Please try to practice more of these kind of questions. I think this is self-explanatory. I don't need to go much into details of this one, ninth one. But still, if anybody wants to discuss, let me know. All okay? Again, 10th one is very much self-explanatory. I don't want to get much into details of it, but if anybody wants, I can discuss. 11th. Again, here also it is uh, pretty much easy to explain, but still, if anything bothers, let me know.
Sir, could you tell the stability of radical?
Sure. Notice. In this case, stability you have always have to analyze very similar to that of carbocation. Now, imagine if this was a carbocation. You see, it will have a strong resonance, right? Very much extended resonance here. Here also some resonance is observed, but here there is no resonance. And resonance is a dominant factor as compared to the other factors like inductive effect or hyperconjugation. So same logic here also. Radicals will also undergo the same type of resonance. This bond would break into radicals, and that would make it into double bond here, and dot will move here. So this way it will start conducting resonance between. Tanish, makes sense? That's why this is a
Yes.
stronger stability form.
Hmm.
Right. 12th one is also quite easily explained, but if you still have an doubt on it, please let me know. What's the basic premise of the question? You need to check out the alpha presence of alpha hydrogen, right? All good. I hope all of you understood why B is showing. I'll take it as a yes. Compounds that produce optically active compounds during the reduction is very good question. This is one very uh, repetitive PYQ here. Okay, so check it out. Initially, there is a double bond here, and there is a chiral center. Most important, this is a transform. Okay, when you add H2 by PD, so now that will get reduced, and you will have this as 1, 2, 3 carbon. Here we have 1 carbon, 2 carbon, and hydrogen. That means the chirality is not disturbed. So the molecule will remain chiral. Okay. Now here when you reduce, we will have this as 1 2 3 carbon. Everything gets reduced. This is propane, and here we'll have 1 2 3. That will also become propane. So this will lose out the optical activity. This will not be optical active anymore. Same way, this is not a chiral center to start with, so we don't even have to discuss about it. Okay, clear? Even after adding it. Next, on adding this here, correct? So you can see this side also it will lose out because hydrogen and hydrogen will come. There will not be any chiral center available after that. So only A will come. Okay. So 14th also is explanatory, but if you have any doubt, I can discuss. Please check everybody. All okay? Ayushi, Sudiksha, did you get this?
Yeah, sir.
Yes, sir.
Right. This is core house synthesis. So I think you should be able to relate that. Next, 15th one. List 1 contains the reactants and list 2 contains the reagent. Again, it's not very difficult, but I think you should be able to understand the nature of the reagents here properly. Okay. So check out. First one. If you have a 3-degree carbon and you are trying to reduce it, that is only possible with NaBH4. Or another alternative one is triphenyl tin hydride. These two are very good at 3-degree positions. Next, if you are just adding hydrogen and hydrogen here, that is done by catalytic hydrogenation. Okay, so Q here and P here. Next one, we are making an allylic substitution. Allylic substitution is done by, NBS. Where is NBS? Yeah, S, here it is, NBS. Last one, it is making an alkene again. Okay, so from there you can make it as an alkane. So alkane is been done by H2 by nickel. That is the important one which you need to check. Yeah? Clear? Right. All of you agree with that, right? Next, this is also pretty much self-explanatory. Okay, check it out once. Right. Please check everyone. If you have it out, let me know. This is Clemens's reduction, Wolff-Kishner reduction. This is Wood's reaction. This is red phosphorus, a complete reduction. All right. So Q would make this one, correct, which is Wood's reaction. Next, you can see P, R, S. These three can make this reaction. And next one will also be P, R, S. All three can make this reaction. And then combining these two, you're getting this one. So that will be done by Q. Please check which option is more appropriate like that. So C, correct. I think this is very simple one. I would like to skip it, but if anybody wants an explanation, I can discuss. 17th, everybody. All okay? Right, all good. Next. Number of coupled products. Okay. Well, this one is an interesting case. This we could discuss. Okay. All right. First case, you'll get only one coupled product, that is ethane. Second case, you can have three different cases. One is ethane, the other one is propane, the other one is butane and propane. Third case, we have one, two, three. So we will have one self, okay, second one self, third one, one, two, three, four, five, six. This three self, then cross. In cross, we can have three carbons. We can have 3 plus 2, 5, 4 carbons also. 4 carbons I have written it. 5 carbons also. We can get this as 5 carbon as well. Okay. So this is the max I can get. So we can get ethane, butane, I mean methane, butane, propane, okay, ethane, then butane. Here we have hexane, pentane, all five you can get. And last one, if you see, this is at an allylic position. At allylic position, the rearrangement is also possible. Got it? At allylic position, rearrangement can also be done here. Okay. So you can see how many we can get. First, let me write down that and show. We have one, two, three, four, five carbons. So one, two, three, four, five carbons. Double bond here and double bond here, and dot will come here. So let me put the dots where exactly they can go. Double bond will go here, dot will come here, another double bond will be here. Correct? So you have to consider as if this is a different compound, this is a different compound. Correct? And if you make the resonance once again, you will get the same compound. So I'm not writing the third resonating structure. Okay. And here we have uh, CH3, CH2Cl. So that is the other third one here. So this one. Okay. This one radical dot. So now if I combine the self, first self, so we can have five here, one, two, three, four, five. One, two, three, four, five. Okay, so double bond here, double bond and double bond. This is the first one. Second one, put it for charging. 1 second. Yeah, second one we have this way, double bond with this dot. Okay, like this, double bond and double bond. Correct. These two, and then we can have a cross one also. So one, two, three, four, like this, and this connected with uh, one, two, three, four, like this, double one and double one. This cross one, right? Next, here again we can have double bond, and this connecting with ethyl. And next one also like this, double bond, connecting with, sorry, like this, ethyl, double bond like this. Okay. And lastly, we will also have ethyl connecting, so butane. Correct. So how many we can get here? You can see one, two, three, four, five, six. So six different compounds we can get. Okay. I was clearly mentioned exclude stereo. Okay. And obviously the options don't have that either. All good, everybody. Right. Next. Let's see the next question type. The third cumulative one. So about the first one. So I'm sure again it is very, very self-explanatory. You should be able to figure it out. Okay. So please do check. So basically you will add here and here When you are adding here, it will become trans. So you just need to check out the trans case here. Okay. Right. So when this will become trans here, so we'll have this as 1, 2. Okay. So here we'll be having double bond 1, 2, 3, 4, 5, 6, 7, 8. At seventh, eighth position, it should be trans. So 1, 2, 3, 4, 5. This is not correct. 1, 2, 3, 4, 5, 6, 7, 8. This should be trans. So this one is correct. Clear? Okay. So it should have been NaNH2 in liquid ammonia. Oh, sorry, my mistake. Here the no at terminal position no addition will happen, no, but because NaNH2 will only make the reduction at substituted alkynes. So here there is no alkyne formation. It will remain as minus only. Okay. So which means the A is incorrect for that reason. You can see 1, 2, 3, 4, 5, 6, 7, 8. Yes. So C is more appropriate. Right. Please check out the second one. Right. It's an easy case. You can notice this. ETO minus, what will it do? Okay. So ETO minus is a good base. Now the structure is like this. How many carbons we have? 1, 2, 3, 4, 5, 6. 6 carbons we have. Like this we have. Okay. And this second position we have a double bond O. Third position we have pH. Last position we have Br. Okay. So ETO minus is very good in making a nucleophilic attack. So we'll get this here. Like this, we'll get this as O minus, OET, correct? And then there is a Br minus here. So that will go and attack here. Correct? Okay. But problem here is this ETO minus when you what do you say? When you take this as an ETO minus, will this be stable? Because you will have two oxygens on the same carbon. So that will not be making it very stable form of it. So then what is the next option we have here? So check out 1, 2, 3, 4, 5, 6. Br here, double bond O here, pH here. Got it? So now again it has two options. That is one, it can take this ATO minus can become a very good base. It can become a very good base and try to pull off this electron from here. And if you get that minus charge, this can make a conjugation, right? So you can see it can make a conjugation here. So you will get a minus charge here, double bond O here, pH here, and then Br here, correct? Then due to conjugation here, you will get O minus. O minus can go and attack internally and remove Br, correct? O minus can go attack internally and make this Br. Now notice this one. We can get this as 1, 2, 3, 4, 5, 6 member ring. Correct? Like this, we have a 6 member ring with one position being oxygen here. Okay. And oxygen's adjacent position here, next carbon here is this one. Here we can get a double bond and pH. But again, this does not look very stable either. What is the other chances? See, ETO minus can take H plus from here and that will be much more acidic. Reason being, this is a stronger conjugate, sorry, this is a stable conjugate base because of resonance. So the same type of resonance you can create with O minus with double bond here and pH and Br here. So this O minus can attack, Br minus can remove. This time you can get a 6 member ring with a double bond here having a pH on it. This will be much more stable form. Okay, sorry, one more methyl here. Correct? So therefore, this is a response you should look out for. So which is B. Clear? So that's how you need to check out all the permutations and whichever you feel like this is the best product, okay, based on all the logics. So you apply that. Here, the most important logic is Nucleophilic additions are usually not favorable with ethoxide. That's why you have to go for, you know, extraction of alpha hydrogens, create a carbanion, and then start pushing the electrons. Okay. This is a very similar question, just like how we have done it earlier just now. So again, a PYQ. This is also a PYQ. It is explanatory on its own, but if anybody has a doubt, I can discuss. Please check. Third one. You just need to check out which one is losing chirality after hydrogenation. Done? All good with that? Right. Let's see the fourth one. Oxymercuration, demercuration. That is the first thing we have to do. And then dilute H2SO4 and heat. So that will give you alkene as well. Okay. So basically, we need to proceed through oxymercuration followed by this. What is here? This is more substituted position where the carbon positive charge can be more stabilized. So which means overall, after forming a mercury bridge here, water will attack on this position, H minus will attack on this position. So let me write down that part here. So how many carbons we have? 1, 2, 3, 4, 5. So we have 5 carbons on which we have a isopropyl here, and then OH will come here and H will come here this way. Okay, correct. This is the way you can have. And then you will be reacting with dilute H2SO4. So it will remove the OH2 here and see how's the structure here now. Like this with isopropyl group here and positive charge here this way. Correct. So in that case, where do we make the double bond which is more stable? This one. This is where you make the double bond. So this has to be the most stable product, which is option C. Check. All okay? Right. So check out this STEM question. All right. Right. So let's see the STEM question here. How is the structure? What is the compound forming? First, you have first one, two, three, four, five, six carbons to make a intramolecular Woods reaction. So as they connect, the methyl and methyl will be adjacent to each other. And we are using one bromine that will be substituted at the most stable position. Thereafter, alcoholic KOH will create a double bond here. Then you are making an ozonolysis, right? Due to ozonolysis, this bond will break. Now count this. These are 6 carbons, 7, 8 carbons we have. So total 1, 2, 3, 4, 5, 6, 7, 8. And on the second carbon, we have double bond O, and this carbon, we have double bond O here. This is compound S. Okay. And then we have R here, which is reacting with Br2H nu once again. So here we have double bond like this. Okay. And isomeric products, you can have a lot of isomeric products here. And that on alcoholic KOH will give you isomeric products as well. So how many isomeric products you can have here and how many isomeric products you can get here? That is the second evaluation. Let's go with the question first. How many deuterium atoms are present in Z? Okay. So if you take this S, let me copy that. Okay. If you take this S and follow that with a long-standing deuterium exchange. So if you recall, for deuterium exchange, all the alpha positions will get, you know, exchanged by this deuterium here. So D and D, D, D and D here. Okay. So how many we are getting? Total 10. So this is the total 10 deuterium exchanges will happen. Next one. how many number of isomeric products of V we can have. Okay, so earlier, if you remember the logic, I told you how to put the Br at different positions as well. So you can see, where do we keep the Br here now? So I can put one isomeric form because that will be repetitive. So like this, double bond. This is one uh, allylic position. This is the second allylic position, and yeah, this one is again repetitive allylic position. So these two are the allylic positions. Now let me put their isomeric forms here. So I can put double bond here, resonating forms here. So you can get dot here, and second case you can get double bond here like this, and you can get a dot here. Okay, these four are the positions where you can have that allylic forms. So we'll write the bromine form for that. Okay, I think there was already one bromine present. No, right? Yeah, no. We're doing it for R only, right? Yeah, correct. So now we can have this as double bond with bromine here and nothing here. Then second case, double bond with bromine here, with double bond here. Third case, with bromine here. Fourth case, we can have like this with uh, double bond and bromine here. Okay. So now notice the first case here. In the first one, how do we get the double bond? See, now this time elimination will happen from this end, because if you make the elimination from here, H plus will go, that negative charge will simultaneously push it, this will push it, and Br will go. That's how allylic follows. So here we'll get double bond and double bond like this. Okay. Now you might ask, sir, why not this will happen? That could also happen. H plus can go from here, minus can push it, double bond can go, and this will go here. So what is the other product I can get is like this, double bond and double. These two are the possible products. These are coming from this one. Okay. Next, if I take this one, let me see what are the other products I can get. With respect to this, again, the same thing could happen. One product is straightforward. On the left hand side, we can have a double bond like this. And the other one will be the same push. Removing H plus from here, double bond can be pushed here. So you'll get a double bond here. So double bond like this. And I can get one more product. H plus can be lost from here. Double bond can be pushed, double bond can be pushed here. So therefore, one more product I'll get. I will get this as double bond, double bond here, and this one. So with respect to this, we'll get three products. You can see these three are the products we can get. And third one, with respect to this one, with respect to this, we can again have products like this here. So double bond can form here like this, which is already a repeated one. So later on we can remove out that. So double bond here like this, and one more methyl. This is also a repeated one, which you already done with the earlier cases. Okay. Next, last one. The last one being this one here. If this has to make double bonds as an alcoholic KOH, you will get double bond here like this. Sorry, this we have done it already. So last one is this one. Yeah, this one. If you do this, we can get it as double bond here and double bond here like this, which is again a repeated form. Or we can make double bond here with these two. That is also a repeated form, correct? Or I can have one more product, which is double bond here like this. Okay, that is also, I think this is the new one. No, this is also repeated one. So check out which of them are unique one. This one this one, and this one, this one, okay, and this one. Okay, these are the five which are non-repeated ones. Clear? Rest all are repeated forms. Please check. Done. The important STEM question, everybody. Next. A scholar worked out the following reaction sequence. So let's see. First, we have NBS. So definitely bromine will come here. Alcoholic KOH. So alkene will come here. Next, bromine has been added. So which means we can have Br and Br being added here. Again, alcoholic KOH followed by NaNH2 and hydrolysis. So which means we'll have a triple bond here. And thereafter we are using NaNH2 once again. So which means you'll have a salt C minus and Na plus. So now please check this through and let me know if you have any doubt in A, B, C, D, E first. All okay? Next. From E, you are making a substitution, so which makes pH, C triple bond C and CH3. And then we are making an addition, so we'll get this as pH because this will make a cis syn addition, so you'll get cis molecule. So this is a major product. So how many primary hydrogens are present in the following compound? So how many we have? Only these three. So those are three. Next. Molecular formula of I. So basically, what did you get it as I here? A, B, C, D, E, F, G, H, I. Okay. We need a reaction for it. So B, where is B? This one. Okay. So we have this B here, which is an alkene like this. This is called styrene. And that when you're reacting with mercury and mercury OMDM, oxymercuration, demercuration, then you see that OH will come here and deuterium will come here by following Markovnikov's rule. Okay. And then when you have to do elimination after cation, you will get double bond here and deuterium here. Because hydrogen is the first one which will leave out of it. Got it? So we need to figure out what is the molar molecular weight of this one. So how much we have? Benzene is 78. 78 plus we have 12 and 12, 24. 78, then 24, and then two hydrogens here. Correct? Sorry, 1, 2 here. And 10, 14. Yeah, one more. Deuterium we have to add. That's it. So how many we got? Total 105. Clear? Next. Check out this STEM question. Again, a good one. But please do let me know if you have any doubt in that. It should be this you should be able to understand, I guess. Check out the ninth one, everybody. Done. Check out on the 10th one. I think these two are easy to understand, so I'm skipping that part. Check out 11th one. Okay, for 11th one, you can just go through the reactions once quickly. What are all the products you're getting here? Okay. So, first one, if you have half a mole of O2 in the presence of Ag, so Ag basically becomes Ag plus 2 moles of Ag plus half O2. That will become Ag2O. And Ag2O is mostly ionic as it comes in front of the cations here. So, I mean, double bond here. So, it will behave like O2 minus. So, then we will have the CH2, double bond CH2 here. And then we have O here coming out as O2 minus. Now, what happens to the basically silver is getting oxidized here and oxygen is getting reduced here. So, that reduced form here will be combining here. But is this that simple? No. Basically, here, if you notice one of the oxygens here, so that will first form from O2, correct? Sorry, let me see the mechanism. G plus, yeah, like this. CH2 double bond CH2 with silver being a complex first. Okay, so this double bond will go, the delta positive will come on both the positions here. And then we have this O minus, O2 minus. So this O2 minus is attacking from the back. Silver is being gone from here. So you'll get CH2 and Ag plus here and with CH2 O minus here. Now silver will take away its electrons and O will attack back. So that's how it will get here. So silver will be gone and this is what you will get. So it will help like a catalyst, but overall it will get to ether form. Next, NOCl basically will have NO plus and Cl minus. So this is the electrophile and Cl minus is the nucleophile. So which is given correct. KNH2, NH2 minus will take H plus from here. That C minus will attack on CH3. So we will get CH3, C triple bond C, CH3. Then with Lindlar's catalyst, it will not give trans, rather it will give you cis. So this is incorrect. And red hot iron tube or red hot copper tube will do aromatization. So this is mesitylene, which is correct. Done with the question. Right. See the 12th one. A on ozonolysis with zinc and water, it is giving this compound, right? Uh, so definitely this carbon and this carbon must have been connected earlier. So we have 1, 2, 3, 4, 5, 6 carbons. So we had 6 carbons here like this, with this being a chiral center with a double bond here. Okay, that's how this compound was. So A is optically active, which is true because this is a chiral center and there is no plane of symmetry. A reacts with Br2 to give racemic mixture. Now this is very interesting. So notice this one. The Br, I mean the methyl will be here. Br can come out of the plane and the other Br will be inside the plane. The second compound will be like this, with this going inside the plane and this coming out of the plane. Okay, these two are the cases. But now you can notice that these two are not the mirror images of each other. Hence, these two are diastereomers. So B is incorrect, A is correct. A react with diastereomeric mixture, which is true. Second, next. A reacts with ozone H2O2 to give dicarboxylic acid, which is true because in case if you break it again, that will become this CHO will become acid in the presence of peroxide. So A is correct, C is correct, and D is correct. All good, everybody? Right. So notice next one. Next one, I guess you should be able to figure it out. It is again a similar question. Hydrogenation will change the chirality or not. Okay. So now you can see in previous year how this kind of questions have been asked multiple number of times. Right. Check out on 14th case here. Okay. This one is interesting one. An alkane A has a molecular formula generates 8 isomeric monochloro derivatives and it can be prepared by catalytic hydrogenation of 5 optically inactive isomeric alkenes with molecular formula C6H14 with alkenes. Okay, so here there was some mistake. It should have been C6H12, I guess. B is an isomer of A and it is also generating 8 isomeric monochloro derivatives. Then correct statement of A and B is. Okay, there's one mistake in here that it should have been C12 here so that it is showing that it is optically, it is an alkene form. Okay, that's one thing it was missing out. Mm, Now, we should have 5 optically inactive isomeric alkenes. So we need to have alkenes here first. Number of carbons are 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 carbons. Okay. So now let's notice how many alkenes we can get out of this. Got it. So this is one alkene here. Then I can have one alkene here. Now basically it should be optically inactive. Okay. So all these combinations we can get here. This one is optically inactive. This is optically inactive. And next, if you have 5 carbons here, so you can get double bond here like this, or I can get double bond here and like this, or I can keep double bond here and like this. And then we can have our double bond inside also, so like this with double bond here. Okay, or I can make double bond here. Lastly, I can make double bond here. Okay, and then we can have 4 carbons, 5, 6 double bond here. This is the possibility we can have. Got it? In case if you make something in the center like this, double bond like this, now this will become optically active. So don't take this case. This case can't be considered, right? That this case you can't take. Now, all of these can give different types of alkenes, but one alkene has to generate 8 monochloro derivative forms, which means it should have been more branched form, isn't it? Then it can produce more. So you can take either this branch form, sorry, we can't take this one, this is chiral center. Okay, so we can have either this as a branched form, correct? Or I can even have this as a branched, another one is um, similar branch we have here. Another one, yeah, this one. No, this one is also not the alkane. Only one branched form, which is this one. Okay, so A must have been this one, like this here. This must have been the A form, which will give 8 isomeric alkanes. Next, he said A, and it also generate 8 monochloric acid of B here. Okay, B of an isomer. It is also generating 8 isomeric monochloro derivatives. Can be prepared by Oh, isomeric active. Hmm. So for this, if this is A, then what should have been B? So definitely B should have been like this, which was optically active, which is coming from optically active, which is an isomer of A. Now this will also give you 8. So this will give 8, this will give 8. Okay, so that's what is the question being asked, right? So now notice this, what of them, what is these are correct options. B can be prepared by catalytic hydrogenation of 4 isomeric alkenes. Now, are we getting this from 4? Please check it out. This one is the compound, but I'm not getting 4 out of it. Only 2 chiral centers. So, which means I can get only 2. Oh, what about this one like this? Sorry. Double bond like this. This one we can get. Yeah. Cis and trans we can get. Uh, and I can also get from this one. Double bond like this. Okay. So we'll get 2 from here, 2 from here, and 1 from here. So actually it should be 5. So that is incorrect. Boiling point of A is more than B. Okay, that is not right either because number of length, if you notice like this, both of them are 5. One is here, one is here. Okay, the one which is more symmetric is this one, so that will have less boiling point here. Sorry, not to do with the symmetry, but to check out on how much amount of length of the chain it will be. So although the chain length is almost the same, a substituted methyl on the center will have more crowding of the alkyl group here. So this carbon has more chains here. So that makes it less boiling point as compared to this one. This is more open. Okay, got it. Next, A A generates uh, A generates 6 enantiomeric on monochlorination, while B also generates 3 enantiomeric pairs on monochlorination. Monochlorination 6. Yeah. So if you notice this one, it should give you 6 monochlorination, while B generates 3 enantiomeric pairs on monochlorination. So if you notice A here, so let me put some structures here. So how many chlorines we can get? One chlorine here, one chlorine here, one chlorine here, one chlorine here, and lastly one chlorine here. So you can see 1, 2, 3, 4, 5, 6. Out of that, this is chiral center and this is chiral center. Okay. Sorry, this is also chiral center, but I think it's saying structural wise or A generates 6 enantiomers. Oh, sorry, 6 enantiomers on monochlorination. 6 enantiomers. So you can see 2 here, and 2 here. So that is correct. So C is correct. Next, B, I mean, first statement is correct. The second statement, B also generate 3 enantiomeric pairs. So let me see the B part here. This is the one. So now, see, we have chlorine here, chlorine here, chlorine here, and chlorine here. So out of this, this one is a chiral center, so it can have 2 enantiomeric pairs. Here there are 2 chiral centers, so that will make it 4 enantiomeric. I mean, total 4 compounds, and that's it. Okay. So again, this is giving 3 enantiomeric pairs, which is also true. A prepared from 2 isomeric ketones, while B also prepared from 2 isomeric ketones. Right. So if you have to have A here, which was like this, and B here, which was like this. So what are the types of ketones I can make here? Double bond O here and double bond O here. These are the ketones I can make. Here, I can make double bond O here, and that's it. Only one ketone we can make it. Okay. So A comes from isomeric ketones, while B also prepared from two isomeric ketones. B is not being prepared from two isomeric, right? Oh, with the chiral center, sorry. The chiral center, that is also two. Here it is only two with structural. So yes, D is also correct. So please go through it once quickly. If you have a doubt, you can ask me now. So now notice the next one. Identify the correctly matched reactants, reagents, and product sets. So you just need to check out whether they are syn or anti-additions. NIA acetone is always an anti-addition, everybody. So now you check out how is this compound. See, if I move around, bromine will come on the same direction. So Br, PH, and PH, which means it is erythro. Erythro plus anti should give us, sorry, cis, correct? So this is given wrong. Okay, the first one was given wrong here. So check out the second one. Second one. Now this time it is 3O, correct? So it is Br here and Br here. Okay, plus anti addition. So that should give you trans. So that is also given wrong here. Next. Here, first one, again, erythro is given wrong here. Uh, 3O is given wrong here, right? Why is it wrong? Oh my God, all of them being wrong. PH and PH. This is erythro anti. Oh, sorry, I only wrote wrong. Erythro and anti is trans. Okay, okay, sorry. Erythro and anti is trans, and 3O and anti is cis. Yeah, sorry. So this one is also correct. Okay, so all of them are correct. So trans, cis, correct. So A, B, C, D, all of them are right. 16th, I don't think much explanation needed there. Please do check. Right, check out 17th one. 17th one, we have a triple bond. Adding here, you will get the cis form, and Br here, you will get a cis form here. Br here, we'll get this as a trans form. Okay, clear? So you can please notice that some of chiral products in P1 and P2. Okay, so you just need to check out here there is a chiral center, here there is a chiral center. Accordingly, you can figure out how many products we can have. That's it. Next, 18th one, number of transition states and number of reaction intermediates. Okay, that's a good question. So please let me know if you want me to discuss, then I'll discuss. Otherwise, we can skip it. Okay, please check. So what all things we'll usually forget? Please check this out. OH2 plus is also an intermediate. That is the first thing we'll usually forget. Second, we will get a carbocation here. That is also an intermediate. Next, in such cases where a seven-membered ring which has a two methyl groups can always be stabilized, that will become very stable compound, so therefore it can undergo ring compression. So as it becomes a compressed ring here, so we will get, sorry, we will get a six-membered ring like this. Okay, and on this position only we have two methyl with a positive charge on it. Correct. So once you get that positive charge, from there you can make a double bond formation. So where do we get the double bond? Here, double bond here. That's it. So that will be the product formation. Okay, so that is the most stable product form. So how many intermediates we got here? So we can see 1, 2, 3, 4. Okay, so 4 intermediates we got. Clear? And how many transition states we will have? Okay, number of transition states and number of intermediates. Sorry. Oh, sorry. This is 3 intermediates only. 1, 2, 3. Yeah, my mistake. I'll just rewrite them. So 3 intermediates and 4 transition states. So that makes it 7. Done. Check out the 19th one. Number of fractions obtained after the fractional distillation is. Okay. See, because you are adding brand solution, which means you're supposed to make this as Br plus and Br minus addition once, Br plus and Cl minus, because brine solution will also contain NaCl. So Cl minus is also a nucleophile here. So take that into the case, and now we have 1, 2, 3, 4, 5 carbons here. 1, 2, 3, 4, 5, and double bond here. So that's where we are adding uh, Br here and one Br here, and then we have one Br addition here and one chlorine addition here. These two are the possible forms. Now, important deal is we have a fixed tritium here. We have a fixed tritium here. So now I got the new chiral center here, which makes this as two compounds. Got it? We'll get this as two compounds here. Okay. Next, if you notice, this one also is a new chiral center that will make it as two compounds. Now, brine solution is a dilute NaCl. Dilute NaCl means what? It is having water also. So water can also act like a nucleophile. So another addition which will happen here is Br plus and H2O, which will act like a nucleophile. So the other products which we need to realize is this tritium, which is present in all of them. And then we have Br here and one OH here. So here also you can see the new chiral center is forming that makes another two compounds. So total we have 6 different fractions we can get. Why 6 fractions? Because none of them are enantiomers. All of them are diastereomeric forms. So as long as we have diastereomeric forms, we will get uh, all the fractions open. All good?